increasingly, shall we say, entangled in recent years, not just in our hopes someday to build fault-tolerant quantum computers, but also in the realm of quantum gravity and quantum complexity. Now, error correction is playing a really central role. And Niko's work has been sort of squarely at the intersection of these two very exciting areas. He's done some wonderful work recently on quantum error correction codes of asymptotically optimal bounds, but that's actually not what he's going to tell us about today. Today he's going to tell us more about a result in quantum complexity, the resolution of the NLTS conjecture, now a theorem, which is sort of an essential step towards quantum PCP. So I will hand it over to Niko.
Thank you very much, Sandy. And yeah, thanks very much, Sandy. And yeah, first of all, let me kind of thank the organizers for the invitation and for setting all of this up. And thanks you all for being here today. Yeah, so as Sandy said, I will talk about the resolution of the NLTS conjecture. So now it's an LTS theorem, but sometimes I will kind of slip and say NLTS conjecture anyway, so please be aware. Yeah, so kind of just to kind of give you a rough idea of what this talk will be about. So the general theme, besides obviously explaining NLTS, will be kind of explaining the interplay between three different domains, and Sandy already kind of alluded to this. So first of all, there's obviously complexity theory. Then there's quantum many-body physics. And finally, there's quantum error correction. And these three domains are kind of very, very close, and they're kind of coming together in this work. But let me kind of get started very, very slowly. So first of all, I think nobody here needs a reminder, but let me remind you anyway. So NP is a complexity class which contains all the problems whose solutions can be verified efficiently. And this verification has two components. So first of all, there's a proof or witness or certificate, and we will always kind of assume that this is a bit string, a finite bit string. And then there's a verifier, which we assume to be a Turing machine. And obviously, you all know many, many examples. So there's a factorization, which is NP, or some stuff like proving a mathematical theorem. And there are so-called NP-complete problems. So these are problems which are so general that they, in some sense, kind of capture the structure of a complexity class. In this case, I kind of care about NP problems. And a non-trivial example of this are CSPs, so constraint satisfaction problems, where we have some set of variables and local sparse checks. And we assign some function, C of x, which is just the sum over all the checks. And the question is, can we decide whether there exists an assignment such that this function is 0, or whether for all assignments this function is bounded from below by 1. OK, so I kind of set this up. I'm sure you all know this, but the important part is like I want to kind of make a connection to quantum in the same way. And the idea is essentially we want to extend notions of proof. And there's two ways of doing this. So first of all, there's a quantum way, and then there's a probabilistic way. So first of all, let's go through the quantum way of generalizing the notion of proof. So in quantum mechanics, systems are determined by something called a quantum state, and they are written in this form. There's like the Greek letter psi in some funny brackets. And this will be our proof. And the verification in the quantum setting will be a polytime quantum computation. And our model for this is not a Turing machine, but a uniform family of circuits. Uniform because we don't want to have we don't want to kind of, cheat and have some difficult problems kind of encoded in the description of the circuits. So it has to be computable by a polytime Turing machine. OK. And the class of these problems is called QMA. So QMA is, in some sense, the quantum analogon of NP. And this was introduced by Kitaev in the late 90s. And similar to NP, they are complete problems. And this is also was essentially kind of immediately figured out by Kitaev. It's the analogon to the CSP problem. And this problem is called local Hamiltonian. So Hamiltonian in physics is something that assigns an energy to a state. Yeah, just to kind of make this kind of analogous, there are kind of checks in this Hamiltonian, which kind of assign an energy to a certain state. And the total Hamiltonian is just the sum over all these local checks. And we kind of care about the ground state energy. And this is actually something that physicists care deeply about. Yeah, so this is something that's kind of their bread and butter. And it turns out that we can define the following decision problem. So given a Hamiltonian or a family of Hamiltonians and some numbers a and b, which are kind of suitably far apart, we have to decide whether the ground state energy is below a. And in that case, there exists a ground state such that its energy is below a, or whether the ground state energy is above b. Yeah. So this is kind of just in analogy to the CSP problem. Okay, and this is again kind of something physicists really care about. And it turns out this is complete for QMA, so probably even hard for a quantum computer to compute in general. Okay, so this was the quantum extension of NP. So let's cover the probabilistic extension of NP. And these are probabilistically checkable proofs. Very surprising, at least to me, almost unbelievably so. It turns out that we don't actually need to know the full proof to check that it's true. It actually suffices to be given some constant number of bits of the proof. Very celebrated theorem is the PCP theorem, which essentially tells us that every NP problem can be converted into a different problem, such that we only need access to a constant number of bits, and we can then accept valid proofs, which probability 1, or this is in the good case, or we might accept invalid proofs, but this is with bounded probability 1/2. Okay. The PCP theorem itself implies for constraint satisfaction problems that it's NP hard to decide whether a solution is actually satisfying the constraints, all the constraints, or whether all assignments kind of have a small lower bound, like a linear lower bound. So in that sense, PCPs give rise to the notion of approximate proofs. Yeah? Because if we know that an assignment is upper bounded, let's say by the number of checks divided by 4, then we can probabilistically verify a proof. Okay, so what we've just seen, NP kind of extends to either QMA, which is a quantum version of NP, or to PCP. So the question is, can we actually kind of put this back together? Like, is there like a quantum version of PCP? And the formal statement is essentially, can we convert every QMA problem such that a verifier which only has access to a constant number of qubits can essentially kind of check whether it's a valid solution or not with constant error probability. Okay, so for example, this local Hamiltonian problem we can kind of convert into this following decision problem. So is there a state such that its energy is 0, or is it true that all states are kind of bounded from below by a constant which depends on the number of terms in the Hamiltonian? Okay. This is again for the same reason. This gives us an approximate proof because everything which has lower energy would kind of be such an approximate proof. Okay, but what this kind of tells us is that approximations should also be very complex. Yeah, and this is where NLTS comes in. So NLTS stands for no, and then low energy, one word, and then trivial states. What do we mean by complex? So there's like very many different ways we could kind of measure complexity. But the one that NLTS kind of refers to is so-called circuit complexity. So we ask for the minimum depth of a quantum circuit over some fixed set of quantum gates that we apply, such that the state is producible by a constant depth circuit. Yeah, so that what the trivial states refers to. Yeah, trivial states are the ones where we only do like a constant amount of quantum computation, and we produce an approximate state. Okay. And yeah, this was kind of observed by Michael Friedman and Ben Hastings. And they asked the following question. So does there exist a universal constant such that, and a family of Hamiltonians, such that any state which has low energy, yeah, so which kind of approximates the ground state, must have necessarily non-trivial circuit complexity. Yeah? So, for example, it could have log n complexity. Okay. And first of all, let me kind of show you why quantum PCP implies NLTS. And this will be a proof by contradiction. So let's assume that quantum PCP is true, and the negation of NLTS is true. Yeah. And let's define the energy as E. Then quantum PCP tells us that given a Hamiltonian, it's QMA hard to decide whether the energy is 0 or lower bounded by some constant times the number of terms in the Hamiltonian. Yeah? Again, I know keep stressing this is kind of important for physicists, so it's kind of nice that like complexity theory kind of tells us something about what cannot be done in a lab. Yeah, and the negation of NLTS is essentially for all constants if there exists some trivial approximation which has low energy. Okay, so now we want to decide whether the energy is 0 or lower bounded. By the negation of NLTS, there exists a trivial state which does the approximation. And in the accepting case, so if the energy is 0, we can classically check, or can classically compute the energy, and we have such an approximate proof. Yeah, and this is not trivial. I will kind of I kind of owe you to kind of show you how to do this. However, in the other case, so if the energy is actually kind of bounded, then it's true that yeah, the energy is kind of bounded below by the number of terms. Yeah, and just kind of by this form, we see that it is actually an NP problem, right? There's no quantum part here. There's only classical computation happening. So we have a classical proof and a classical verification for a QMA problem. And assuming that QMA is strictly harder than NP, yeah, there's more power in quantum computers than it is in classical computers. This is a contradiction. So yeah, I still kind of owe you this statement, like why can we actually compute the energy or approximate the energy classically? And this is done via, let's call it the light cone argument. So let's say we have some operator A, then and we want to kind of evaluate its energy, then or kind of evaluate what this operator is. In quantum mechanics, we have to kind of perform this trace operation, and let's say our state is prepared by some circuit U. Then we can do some algebraic manipulation. We just kind of use the cyclicity of the trace, and we can write this in this circuit. So this is our operator that we want to evaluate. Here's our circuit that prepares the state, and here's our state itself. Then actually the value of the value of the operator A, or its action, is kind of bounded by this light cone in the circuit. Yeah? And here we have a unitary and its inverse. So these all cancel out. Yeah? And essentially, we only have to evaluate this light cone. Yeah, and let's step back. And it turns out that if this light cone is of constant size, then we can definitely do this with a classical computer. Yeah? There's no exponential blow up due to quantum. Okay, so that's the NLTS conjecture. And if this conjecture had been false, then quantum PCP would have been trivially false. Yeah? And I think it's still open whether quantum PCP is true or not. Okay, but yeah, it turns out that NLTS is actually correct. Or it's a true theorem. So this gives us partial evidence that quantum PCP might actually be true. And the way we show this is by constructing these Hamiltonians through quantum error correcting codes. So these are codes which are used actually to correct errors in quantum devices. Okay. Okay, before I dive into this, let me kind of give you like a nice implication for quantum many-body physics. So effect of life is that quantum mechanics does not actually apply to our scale. Yeah, so we don't actually see any quantum effects in everyday life. There's no Schrödinger's cats walking around. There's no weird correlations, quantum correlations that we can observe. So why is this? This is because have entanglement and superposition, they all kind of get washed out by a process called decoherence. Yeah? So if we have some quantum system, so I kind of draw these qubits here as these little balls, and the state is essentially like the position on this ball. And let's say they're entangled, so this is kind of indicated by these squiggly lines. So if temperature is non-zero, then all these entanglement connections get kind of broken up. Yeah? So we don't see any quantum mechanics at non-zero temperatures. This is also not exactly true, but at large scales, this is true. Okay, but is this universally true? Like, could we kind of imagine situations where this wasn't true? And NLTS actually tells us it isn't universally true. So NLTS implies that there exists a physical system where the Gibbs state, which is just a state at non-zero temperature, is non-trivial, meaning it cannot be approximated classically. So the circuit complexity of this Gibbs state is lower bounded, and therefore it has non-vanishing global entanglement. Yeah? So this is like a kind of universe where entanglement is really a fact of life. Okay, so just to kind of motivate you, complexity theory is actually very useful for kind of answering questions in quantum many-body physics. Okay, more generally, there's a whole set of conjectures which are all interrelated, and this is a diagram which I've taken from a paper by Elder and Harrow, which I really like. And this diagram you have to read in the following sense. So there's all these conjectures with all these abbreviations, and if one conjecture is kind of inside another conjecture, it means it implies this other conjecture. Yeah? So there's something called NLETS, yeah, which is like the broadest one, and it is implied by CNLTS, which is implied by NLTS, which is implied by QPCP, which we have already seen. And then there's some other conjectures which have to do with the existence of certain codes. Yeah? And I will kind of brush over this or kind of touch on this in a minute. Okay. So the NLETS conjecture, which I actually won't even define, so this is essentially like a weaker form of NLTS, was proved first by Elder and Harrow themselves in 2017. And then there's like different constructions due to Nierke and Vasirani and Yuan, and also due to Anshu and Nierke. What was immediately obvious here was that all these constructions essentially kind of correspond to physical systems which are low-dimensional and Euclidean. Yeah? So they live on some have letters. And we already knew that this cannot actually give us NLTS Hamiltonians. So there's this argument that we can take any, let's say we take some lattice, and we subdivide this lattice into L by L little pieces. And by subdividing it into these constant-sized blocks, it is actually possible to prepare a state in constant depth, yeah? Because it's just constant size, so we can prepare it in constant depth. Yeah, so we can do this. And the energy price that we pay corresponds to the boundary, right? Because we only prepared the bulk correctly, but the boundary kind of we kind of just ignore. Yeah, so there might be some energy price, but the important part is the energy price actually only scales with 1 over L times the number of qubits n. Yeah. So the energy penalty again is kind of proportional to this boundary, and because in lattices bulk always kind of scales better than boundary, yeah, we can kind of always kind of choose an L such that it beats our universal constant. Yeah. So again, yeah, please go ahead.
Does this argument not also apply to the NL ETS? Like, is it just saying that the only terms you will violate are the ones that like cut between the cells? Right?
That's true. That's a very good question. How does NL ETS so?
I also thought that those were not. Maybe I'm misremembering.
Okay, let me get back to you like in a second. Maybe after the talk. Yeah, I can't think of it right now, but yeah. Okay, yeah, and just to kind of give the reference. So this was an argument given in Aronov Arad Vidik. Okay. Okay, so let me kind of go to the next step. This is the combinatorial NLTS conjecture. And here, instead of kind of asking for low energy states, we are considering states which violate terms. Yeah, so really kind of count the number of violations in our quantum constraint satisfaction, like in the clauses, the quantum clauses. Yeah. So why is this a weaker statement? Because the feature or annoying thing about quantum is there's like some level of continuity to it, and we can imagine states which are kind of these like low-level modes, yeah, which kind of vary very slowly, and they all kind of violate these terms by very, very little. Yeah. Whereas in CNLTS we really ask about like the number of terms which are violated. Yeah. So that's kind of the difference. So it doesn't really kind of capture quantumness in some sense. Like, it doesn't really capture this continuity. Okay, but CNLTS Hamiltonians do exist, and this actually kind of happened like roughly a month before NLTS got solved. And the reason why I kind of bring this up is because actually the idea is very similar, but it kind of already has like some of the features, and they're kind of easier to explain. So the idea is essentially to construct a Hamiltonian via something called a tensor network. If you don't know what this is, don't worry. But the important part is this tensor network implements a classical code. Here the construction actually has the right geometry, which is kind of expected. So there's some kind of underlying expander. Yeah? And I guess you all know what expanders are, but let me kind of define it anyway. So these are well-connected and sparse families of graphs. Sparse just means every vertex is connected to a constant number of, like bounded by a constant number of vertices. And well-connectedness kind of refers to the following property. So if I take any subset S, and I look at the edges which connect S to its complement, then this kind of scales kind of favorably. Yeah. So like the minimum over all these subsets is kind of bounded. Okay. It turns out that expanders are useful for lots of things, and not just to make nice codes. This was observed by Zipser and Spielman. So they kind of take one of these expander graphs, and they assign a local code around each vertex. And they showed that this actually gives us like optimal code in some sense. So the idea really is we take this graph, we put a bit on every edge, and then we check that around each vertex we always see a small code which is of length of the degree of the vertex. Yeah. So every vertex locally sees a code word of some kind of small block code. And so why is this necessary? So first of all, if we just take the expander itself, then this would give us a terrible code. So if we just take the graph code here, then just every cycle would give us a code word, and this would have a very, very small distance. And I will show this in a minute, but maybe I should kind of mention. So this is called also the Tenor construction due to Tenor. And one nice thing is that this is actually something that's kind of well studied in mathematics. This was observed by Meshulam. So this is something called homology with local coefficients in mathematics. Yeah? So these kind of Tenor codes, mathematicians kind of deal with them on a regular basis, but in a completely different context. Yeah, so, and I will kind of denote this in this following form. So C stands for code, and then X is the graph, and L are these local codes that we kind of see. Okay, so the point I was about to make was why do these have linear distance? And I think this is kind of like a nice. So the proof is very short. So I kind of, if you haven't seen this before, then please look it up. It's kind of very beautiful. But in this kind of like toy picture, let's say we have this expander graph, and let's say we have a code around each vertex which has distance 3. Let's kind of mark all the edges which have a 1 with a red edge. And let's say, yeah, what are the code words of this, which are non-zero? Then we have to kind of draw some subset of edges, such that each vertex has at least 3 incoming edges. Yeah? And you can easily see, if you kind of start drawing, this distance of the local codes, yeah, the fact that we have to kind of have, like, if we have like 1 incoming edge, we have like 2 outcoming edges, yeah, plus the expansion of the space kind of work against us to kind of draw small, draw a small number of edges. Yeah? And this means that the underlying code must have lots of, the underlying code word must have lots of ones, so its Hamming weight is large, and this means it's, yeah, okay, and you can kind of prove that this is actually a constant fraction of the total number of edges. Yeah? So this is a good code. Okay, and then CNLTS, again, I won't kind of go through all the kind of technical details, but the idea is essentially we take such a code and we define from it local Hamiltonian. Yeah? And the ground state is essentially determined by all these code words. Yeah? Which look very complicated, but yeah, which are kind of, yeah, this kind of linear subspace of edges. Okay, and now comes really the crucial observation, which kind of underlies the whole thing. And this is that if we look at approximate code words, yeah, so we take our Zipser-Spielmann expander code, and we look at kind of maybe the set of almost code words which have just violate like a small fraction of terms or of checks, then the following is true. Within the total Boolean space, yeah, there are our code words, which are these kind of black dots, and then there are our approximate code words, which are these kind of green bubbles. Then it's true that either these bubbles, either these approximate code words are close by, so they kind of belong to this kind of cluster, and these clusters are kind of far spread out. Okay. So you might kind of observe there are some clusters which actually don't have any code words. So did I forget to kind of draw code words? Actually, this is not necessarily the case. So you can kind of imagine situations where you have a code, where you have a cluster of code words, approximate code words, but they are not kind of centering around an actual code word, which would kind of imply local testability. And this is actually not the case. So just to kind of give you like a silly small example, I will call this the dumbbell repetition code. So imagine we have like 2 spheres, and we put on we kind of connect them by a very thin tube. Yeah? And on these spheres, we define a repetition code. Yeah? So we just kind of put bits on it, and we just kind of measure parity between them. Then any approximate code word is essentially one where let's say we have like all zeros, and then we kind of flip some things. Then we have this kind of like small island. Yeah? But imagine we flip like a whole side of one sphere and like leave the other one the same. Yeah, so we have like all ones on one side, all zeros on the other side. Then we only have like a small violation here, right? And we kind of wiggle this violation around, so it kind of gives us a cluster. But they are still far away from any actual code words. Yeah, so this is kind of that's the explanation of that. Okay, so the proof idea of CNLTS is actually the same as for NLTS, so I won't kind of go through it. Just kind of, I know, spoil you a little bit. So the clustering essentially kind of leads to a spread of some probability distribution. If we kind of do our measurement, we kind of get some result with some probability. Yeah, this will be a well-spread distribution. And this well-spread distribution then leads to a circle lower bound. That's kind of the idea. Okay, so let's kind of now move on to actual NLTS. Surprisingly, the proof is based on the exact same observation as for CNLTS. but it uses a very different construction. Okay, so instead of using classical codes, we actually use quantum codes. And again, I kind of appreciate that not everybody kind of knows what a quantum code is, but like very roughly, the idea is we have just some set of qubits. Yeah, again, I kind of draw these little spheres, and the position on the sphere gives us the state of our qubit. And this gets mapped into a larger number of physical qubits. And it doesn't get mapped like one-to-one, but it gets mapped into like non-local degrees of freedom. Yeah, so there's like some degrees of freedom which are kind of spread out and kind of live in the kind of space of entanglement. Yeah, the whole business of quantum error correction is essentially kind of spreading them out as much as possible, such that if there's like small disturbances locally, it doesn't affect the global encoded information. Okay, there's also a notion of distance. So usually a code has 3 parameters, n, k, d. So n is the number of resources, the physical qubits. K is the number of encoded qubits. And then d is the distance, which kind of tells us how good the code is. And here, the distance is essentially the minimum number of single qubit errors that would kind of change the encoded information. Okay, and error correction was essentially invented by Peter Shor, actually shortly after his factorization result. And Shor essentially showed that there's actually 2 types of errors that we have to be able to correct. There are normal bit flip errors, so-called bit flip or X errors, and then there's phase errors. So intuitively, you can kind of imagine on a sphere there's like 2 degrees of freedom. We can kind of move in 2 directions, and these are the directions we have to be able to account for. Again, kind of appealing to intuition, a quantum code is essentially 2 classical codes kind of put together. Yeah? So we have to be able to kind of correct these 2 types of errors. So we need 2 parity check matrices, or 2 sets of parity checks. There is a very harmless-looking condition, but actually that makes quantum coding theory very hard. So due to Heisenberg uncertainty, we have to assume that the checks are compatible with one another. And it's kind of expressed as this condition that checks in one have to be code words of the other code. Okay. Yeah, again, kind of it's the same spiel as always. So we have like some kind of sparse set of checks, and they give rise to kind of define some energy penalty. So they give rise to some local Hamiltonian. Okay, but we can't just take any old quantum code. Otherwise, NLTS would have been proved a long time ago. We need something much more aggressive. So we need good QLDPC codes. So again, LDPC refers to sparse checks. We also need that the number of encoded qubits scales linearly with n. Yeah, so best we can hope for in terms of encoding asymptotically, and also the distance has to be linear. And that was really a hard nut to crack. I won't go into that distance, into that history, but there's been like a long time actually no progress on the code distance. However, actually we do now know how to construct such good codes, and this is done via something called balance products. And this is a tool that's kind of loaned from algebraic topology or homology, and it's somewhat technical. So let me kind of appeal again to intuition. And there's like a topological way of kind of thinking about this, and I can kind of draw pictures. So how can we do this? How we kind of talk about codes in a topological way? So let's consider I have a repetition code on 3 bits. Yeah. So the code words are just 0, 0, 0, and 1, 1, 1. The code words are elements of the kernel of the parity check matrix, and this is the parity check matrix. However, I can assign a graph to this parity check matrix, which is just this circle graph, right? I assign edges to be bits and checks to be vertices, yeah? And then you see that the vertex edge incidence matrix is exactly this parity check matrix, yeah? So this is a way you can kind of start talking about codes in a topological way. Yeah, so let's do that. So from now on, when you see a circle, you think repetition code. What I can do with circles, I can take Cartesian products, or like with topological spaces generally. I can take 2 spaces. I take the Cartesian product, and it turns out if I take 2 circles, I get a donut. Yeah, I get a torus. Yeah, and maybe you have heard of this. So this is the famous Tori code of Kitaev. This is like the standard example of what a quantum error correcting code is. If you just see this and you don't know about quantum error correction, then you might think, okay, so what? But actually, it's kind of somewhat surprising to quantum error correcting people. You tell them like the Tori code is essentially like the quantum version of repetition code. And this was kind of figured out by Tillich and Seymour. This is the case. Okay, so now what are the parameters of this code? Yeah. So first of all, the size is kind of given by the input sizes just multiplied. Yeah. So this is what happens when you kind of take Cartesian products. Yeah. Things just kind of now blow up quadratically. However, it turns out that the code words of the quantum code are kind of lifts from the classical codes. Yeah. So if I have a code word here, so 111 is a code word, and this kind of lifts into a so-called logical operator. So I didn't kind of define this, and I won't kind of go into this, but this is what this is. Yeah? So this is like some observable on a system which reveals information about the encoded information. Okay, and because this is the case, the distance is actually just bounded by the distance of the two input codes. Yeah? So in particular, since the blow-up here is quadratic, the distance here has to be only the square root of n. Yeah? So pretty bad. Okay, so now comes like 2 slides for experts. So don't worry if you don't if there's something you don't understand. So this is like this kind of like homological algebra description of this whole thing. So again, we take our classical code. So this is just a map from bits into checks through the parity check matrix. Yeah, before this were our edges and our vertices in our topological space. And we can define a tensor product. So this is the tensor product of homological algebra. So we take 2 codes, like C and C prime. We arrange them like this. We take tensor products between the elements. Yeah? And voila, this is essentially what the Cartesian product is. So before we had 2 one-dimensional objects. So we had 2 circles with edges. And the product of 2 edges gives us a face, like a square face. Similarly, we get vertical edges and horizontal edges by products of vertices and edges and vertices. And we get vertices which are products of vertices. The important thing is, now we also know what the incidence relation is between these objects. Yeah? And this incidence relation essentially gives us our checks. Yeah? In the algebraic language, this is called the first homology group. But the parity checks themselves are very easy to understand. So it's essentially just checks between edges and faces, or edges and vertices. Okay. But as I said, we're kind of still, I mean, essentially just a different, more abstract description of what I just kind of told you about this Cartesian product. So how can we increase the distance? And the main observation here is, if the 2 codes, C and C prime, share a common symmetry, kind of symmetry given by a symmetry group G, then we can quotient out the symmetry. Yeah? So they're kind of, so we kind of reduce the overall size by doing so, kind of going through to a quotient space. And if our symmetry group is large enough, so if it kind of scales with n, then the number of qubits that we get, we don't have this quadratic blow up, but we kind of stays linear. But remarkably, the homology kind of stays unaffected. Yeah? So the actual code words stay the same size. Yeah? That's kind of the trick. Okay. In previous work, myself and Jens Eberhard, who is a mathematician at the University of Bonn, realized this was a case kind of based on earlier work by Matt Hastings and Jong-Won Ha and Ryan O'Donnell. And we conjectured that kind of this construction is essentially what gives you good QLDPC codes. So in particular, we kind of thought about kind of taking, okay, we need like some very aggressive expansion. So we need Ramanujan graphs, and there's a group PSL acting on it. And yeah, so this was our conjecture. So it kind of look like this. So we have our expander graphs. We take this balance product rather than the tensor product, and then we kind of get like this kind of object. And this was proved by Panteleev and Kalachev. So they kind of proved, so we already kind of knew that the encoding rate will be good, but again, distance is like really the hard part, as usually. And this was really a remarkable feat of them. They kind of showed this. Actually, they showed even more, and this is actually even more remarkable, so it's just like a side note. So if we take the second homology group of this object, not the first one, so we don't put degrees of freedom on the edges, but we put them on the faces. And this gives us the so-called C-cubed LTC codes, so good locally testable codes. And this was also observed by Dino and others. Okay, so okay, let's kind of now sketch the proof of NLTS. So now we have like everything kind of set up. We have these good QLDPC codes, which give rise to a set of Hamiltonians. So now how do we actually prove NLTS? And essentially kind of follows through this technical lemma. So let's assume we kind of take some subset of qubit positions, S1 and S2, and we look at the probability distribution, the psi, which is induced by psi itself, which we obtain by just kind of measuring on our state. If we have good support on both S1 and S2 in our probability distribution, then there is a lower bound on the depth of the quantum circuit, which is kind of given by the distance between these distributions. Yeah. So if we kind of control this distance, we get a logarithmic lower bound on the circuit size, circuit depth. Okay, so this is kind of like the main technical tool. So in order to prove NLTS, we have to kind of show that all low energy states give rise to these well-spread distributions. Okay, and this is where this property comes in that we've seen before. So this is about the clustering of these approximate code words of these codes. The idea is essentially, since we are talking about quantum codes now, there's this kind of type of degeneracy inherent to it. So we need like a slightly different type of metric. We can't just look at Hamming weight, but we have to look at Hamming weight up to what is called a stabilizer. So yeah, if you don't know what this is, again, kind of don't worry, but just as a comment for the experts in the crowd. So yeah, so we have essentially the same picture. So we have code words which kind of sit at this kind of black dots, and then we have approximate code words, which are these kind of green blobs around them, and these kind of clusters, we have to kind of show that they are kind of well spread. Okay, and if we measure the low energy states, let's say in like one of the two bases, then we will be mostly supported on like this kind of cluster, and this gives us our distribution. Yeah. So immediately we see that in order for this to be true, we require linear distance. But again, as a comment for the experts, we do not in fact need quantum local testability, and that was kind of like the surprise here, because we already knew that QLTC would imply NLTS, but it turns out we kind of somewhat evaded QLTC, and in fact QLTC is still an open problem, and this is exactly due to this issue, or not issue, but due to this fact that not every cluster needs to contain an actual code word. Okay, so now what's left to show is that distributions are not concentrated on a single cluster. And here we can use another technical lemma. So we use the uncertainty principle itself, that if we have two sets, S and T, which are subsets of the outcomes that we can obtain by measuring, then the state again induces two probability distributions, this time in the two different bases, so dx and dz. Again, this is kind of technical, and the distribution in the x basis is bounded by the distribution in the z basis times the average size of the two sets. So in particular, if the z distribution is concentrated on some cluster in the z basis, let's say 99 over 100 of the mass is on S, then any cluster in T must be spread. Okay, and this is why we require the constant rate. Yeah. Okay, so yeah, that's the kind of the essence of the proof. So let me conclude. So first of all, we've seen that good QLPC codes give rise to NLTS Hamiltonians. In our current version of the paper, we essentially use the distance proof of Livry and Seymour for this. It implies that thermally stable entanglement is possible for physical systems below a critical temperature, which is kind of a neat thing. So they can kind of use complexity theory to imply something in quantum many-body physics, which otherwise would be kind of is unknown how to prove. And most importantly, this kind of leads evidence to quantum PCP maybe being true. And yeah, with that, I thank you for your attention.
So before people proved the PCP theorem, they had several less ambitious characterizations, like what if you have logarithmic many, reads or locality, or character something higher than NP, or holographic proofs and such. For quantum PCP, is there any such effort?
That's a very good question. So the issue is essentially that like a lot of the approaches for like classical PCP don't carry over into the quantum realm for like various like various technical issues. Like for example, like the long code really doesn't exist in the quantum realm and so on. So that essentially kind of it's like a hindrance in kind of adapting, let's say, ideas from the classical world. And I would say, like, I mean, NLTS is just like in some sense, it's just a stepping stone, but it's like in the classical realm, this would be like a trivial statement, but already that is kind of hard to prove. So I think we are just kind of at the beginning of kind of tackling quantum PCP, really. Yeah. So I hope this kind of answers your question, but yeah, it's essentially like a lot of essentially none of the like classical ideas kind of carry over into the quantum world trivially.
For example, if you just simply allow more locality.
Oh, sure. Okay, but even then we don't know how to kind of tackle that. So that's that's essentially the answer. Yeah.
Thank you for this talk. You said you had this slide where you showed that the result. Well, please allow me to speculate a little bit in the physical direction. You said that the Hamiltonian is possibly a Euclidean space, and this is consistent with what we remain in geometry to describe the universe, for instance.
Yeah.
And so, what kind of which temperature is it?
Oh.
Is it physically realizable? Do I have any?
Okay, so first of all, okay, so I think one thing is, so since these kind of graphs embed nicely on Riemannian surfaces, and since this is actually a topological construction, it's still Riemannian, yeah? So there's still like, everything's kind of still describable on like some kind of smooth manifold. And it's like some kind of horribly, like since it's like an expander graph, it has to live in some hyperbolic space. So some kind of like really horribly twisted hyperbolic manifold that we're talking about. I have not computed the actual temperature. And I think like the bound would be pretty bad. I think Anurag for fun kind of plugged in some numbers, and I think he got like something ridiculous. I don't really remember the exact temperature now. Okay, yeah, but actually he did actually for fun plug it in. But I mean, again, this is kind of just like a really like a bound, and also it's kind of really aggressive. So okay, so if the question is kind of I know hinting towards like kind of is there like maybe some NLTS Hamiltonian out there? I don't know, probably not, since also like I mean it kind of really depends on being four-dimensional, I would guess. So yeah, so I don't really expect kind of I know somebody actually observing this in a lab or elsewhere in nature, but I think it's a reasonable question to ask, and now we know the answer. So the thing is, this is like the only way we know how to construct these codes. So, but like in the proof itself, no, actually not. Yeah. So I mean, okay, I could actually, I mean, reasonably, I could imagine like other constructions. So you could imagine like some other like expanding high-dimensional object that you kind of equip with this homology with local systems. So where you kind of, I know, plug in, let's say you have like some high-dimensional expander, and instead of kind of doing like normal homology on this, you kind of put in like local codes everywhere. Yeah, that's like the Zipf/Breuckmann construction. I would imagine this would also kind of give you such a code. Yeah, but I mean, the thing is, what's really nice about these like tensor product constructions is that we can kind of pull back onto like one side or the other. So this extra structure actually kind of makes it possible to actually prove these kind of things. Yeah, it would kind of require new ideas to come up with new good LPC codes. Yeah, quantum LPC codes.